Welcome everyone. So this is our 103rd live stream geometry. We had a few before this that I didn't record for various reasons, but glad to be recording this one. So we have 3 people here with us now, and today I am going over problems from Komal. So it's a Hungarian math journal. So I chose 5 problems from that. And then I chose 1 problem from the Vietnam Math Olympiad this year, which looks pretty hard. So hopefully we will enjoy it. And if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video. We meet every Sunday at 8 a.m. US Central Time. All right, so I'm going to share my screen. Here is the first problem. So I think this might have been from a previous year. I try to find the problems from 2023, but I'm not sure if they're out yet. So we have a triangle ABC, and D lies on the angle bisector. So D is any point on the angle bisector. Hey Shreya, thanks for joining. I'll draw, so we end up drawing the circumcircle. So I'm going to draw that right now. And I feel like I might as well draw the midpoint. We'll call this M. BD and AC, we see where they meet the opposite sides. For BD and CD. E and F. And the circumcircle of ABC meets EF at P and Q. And then we draw the circumcenter of DPQ. That's kind of interesting. And we want to show that OD is perpendicular to BC. All right. So let's make this look a little nicer. How do I make that circle smaller? If I move D higher, I guess it gets smaller, but really I think I just need to shrink the diagram. So we want to draw the circumcenter, and we want to show OD is perpendicular to BC. All right. Let me move it down so I can make this bigger. Something like that. All right. 1, 2, 3, 4. And it looks like Nguyen is joining. Hey Nguyen, thanks for joining. Or he's not on audio yet.
I think we should get rid of the circumcenter. It's just a bit like it doesn't really matter. You could formulate the problem of having isogonal lines.
Okay.
So if you draw a line through D perpendicular to PQ, then you would
PQ or BC?
Actually draw both.
Okay.
You would want to show that those 2 lines are isogonal in angle PDQ.
Okay.
That is
So,
just equivalent.
okay, so we can kind of hide this circle and make more room if we do that. Let me draw this. And let me draw the foot of the perpendicular here. Okay, so really it's kind of like we want to show, we could reduce the problem. I'll probably add that part of the diagram back in when I write up the proof in the end, but for the time being, we want to show that VH and VG are isogonal.
Intersect PQ with BC.
Okay. Yeah, that's a good idea, and then that'll give us a cyclic quadrilateral.
Yeah. So you would get that GDHA is cyclic.
Yes.
And also it is cyclic with that intersection point, obviously.
Yeah. So IA, we're saying, would pass through the midpoint of this arc. Sorry, so why is A on that? So is A being on that circle equivalent to these being isogonal, or you can prove that A lies on it?
We can prove it.
Okay.
Just as you noticed, IA passes through the midpoint of the arc.
Okay.
And you can just notice that AD and AJ are perpendicular since they are internal and external bisectors.
Okay.
So you get 90-degree angles, and that's it.
So how do we know IA passes through the midpoint of arc BAC?
Okay, you can do that by projective geometry.
Okay.
You can, if you intersect AD with BC, that is a fixed point.
Oh, it's harmonic. Okay. Yeah.
It's harmonic.
So IBKC is harmonic. So since that's an angle bisector, yeah, that has to be perpendicular. All right. Hey, Con. Hey, Nguyen. Thank you both for joining. Okay. So if we can show DH and DG are isogonal in QDP, that would solve it. And looks like we have someone else joining. All right. So, hey, Chuan, thanks for joining. Is this your first time on the session?
Yes, it's my first time.
All right. Were you the one from Croatia?
Yeah, I'm from Asia.
All right. Good to meet you. So yeah, this is our first problem. For everyone who just joined, so there's more to the diagram. Like it says to draw the circumcircle DPQ. So I hit it, but basically we figured out that if I did draw it and I drew this point right here, the problem is equivalent to showing that VH and VG are isogonal with respect to PDQ. to just hit it to make the diagram easier, but that would solve the problem. All right.
Okay, I found a lot of new stuff on the diagram.
Okay.
Intersect PD and QD with the line BC.
Okay. PD and QD.
Okay, now what I found is that we have collinearities LQ and J.
LQ and J.
Yeah, and also NP and J.
Interesting.
Also, Q, P, and L is cyclic, and A is the Michael point of that quadrilateral.
Wow, that's a lot of information.
Yeah, and I don't know, didn't prove any of it for now.
Okay. All right, let me turn the volume off on my computer for just a sec. All right.
Okay, I think we should do root BC inversion
Okay.
because of the following thing. I just checked and it looks like Q and N invert to each other.
Q and N invert to each other.
Yeah, that would basically mean that AQ and AN are isogonal in line in angle BAC, which is looks true.
AQ and AN are isogonal.
Yeah.
Let's think about what that would mean. That would mean that this would be like parallel to BC, where this intersects. Interesting. Okay. Okay, so if we try root BC inversion, then B and C would be swapped. So root BC inversion followed by reflection about the angle bisector, right? So yeah, isogonal, two lines. If this angle and this angle are equal, so if angle SRU equals angle TRV, then we say like RU and RV are isogonal with respect to angle SRT. So yeah, it's a fancy way of saying something that's kind of simple. So when I say we want to show basically, Stefan was saying that it turns out that if you look at angle QAN, then AB and AC are like isogonal with respect to it, because angle QAB is equal to angle NAC, and we think we might be able to prove that. So that's what that means. All right. So a root BC inversion would swap B followed by reflection, it would swap B and C, right? And we think it would also swap Q and N, is what you're saying. So it would take D to a certain point. E and F might be a little tricky. It would take the circle to itself. I wonder if it really, because let's see, if we want to show that these are isogonal, let's see. So it's basically the same as saying QDH is similar to DLG, right? Yeah. It's equivalent to this being cyclic. If we can show LQPN is cyclic, basically we've solved the problem. So yeah, maybe I should hide this for now. And yeah, it would follow that A is the Mikkel point, but yeah, once we show that cyclic, we've solved it. So IALD. So let's see, if it is the Mikkel point, then we also have AQLI as cyclic. Is that obvious? And also IAPN. And I think there's one other that would be cyclic.
No, I think we can try another way.
Okay.
Can you write the tangent at A of ABC?
Okay.
Yeah, and let's CD cut the circle ABC as X.
So this point, did you say X?
No, I mean CD.
Oh, CD.
Yeah, cut the circle ABC at X.
So like the circle ABC, it only touches it at one point, right?
Yeah, and I mean CD and BD.
Okay, so we want it to intersect, see where it intersects both of those, is what you're saying. CD and BD.
Yeah, no,
Okay. So this and this.
yeah,
Okay.
no, cut the circumcircle of ABC.
Oh, but like the tangent, oh, do you want the tangent to this circle A? Sorry, let me check the chat. CD and BD, oh, we want to just see where they cut the circle. Oh, I thought you were saying, did you want me to draw the tangent or,
Yes, you should keep the tangent.
okay, I'll keep it. Hold on just a second. All right.
Yeah, and by the Pascal theorem, we can prove that RS, PQ, and AA are concurrent.
Okay. RS, so basically, okay, they meet this tangent at some point T. Okay, that lies on that. All right, by Pascal's theorem.
Also, you can, in this picture, we know that TD is parallel to BC.
Yeah, we should prove DT parallel to BC.
Okay.
Now we can calculate TR over TS
Okay.
is equal to AR over AS squared.
Okay.
Yeah, and now I want to prove DT is parallel to BC is equivalent to DT is the tangent line at the of the circle RGS.
Okay. So if we prove that DT is parallel to BC, then you said, what was the next thing you said after that?
DT tangent to DRS.
DRS. Okay.
Yes.
And would that solve the problem?
Yes.
Okay. Because then we'd have like TD squared, or I forget, what is it, like T
TR.
AR over AS squared is TA over TS or something?
TR over TS.
Okay. All right. So we have to show that TD is parallel to BC.
Yeah, and that is equivalent to TR over TS equal to TR over TS all square. So we want to prove that AR over AS is equal to TR over TS.
Okay.
Yeah. AR over AS, we can invert to sin ACD.
ACD.
Yeah, let me.
Okay. AR over AS is sine ACR over sine ABS. And dr over ds is dB over dC, which is sine BCB over sine BBC. Interesting. Oh, and then trig Ceva finishes it, right?
Yeah.
Okay. Interesting. So AR over AS is equal to dr over ds. And those are both equal to like if you square both, it's equal to TR over TS. Do we still have to prove that this is parallel, or we've proven that?
When we have TD parallel to BC,
Is that
we should notice that QP is the radical axis of ABC and DBQ.
okay? So that's the radical axis.
Yeah. And we have TIA square equal to TQ nhân TQ
Okay.
TQ
All right.
TB.
All right.
Yeah.
I like this. So I'm gonna write this up. This is very interesting. Yeah, this is probably a good time just to add back in O. All right. Okay, so let CD and BD meet to circle at R and S. All right, and then let by Pascal's theorem RS. I forgot to draw this. RS PQ and the tangent at A meet at a point T. Meet at a point P. All right. And then, so by the radical axis theorem, we have RS, PQ, and okay, so we're using the radical axis theorem on this, and ABC. All right. So ARB SAC. All right. And then by the radical axis theorem on ABC, DPQ, and DRS, we find TD's tangent to DRS. TD is tangent to DRS. Let's think about that. Is that obvious? So basically we're saying T lies on the radical axis of both of these circles, right?
No. We should prove TD tangent to DRS first.
Okay, we have to prove that. It's not obvious from this. Okay. But if we can show TD equals TA, that would prove it.
Yes.
And we can calculate this angle.
You would need to show that TD is parallel to BC.
Right.
If you know that, you can angle chase TA equal TD.
Yeah. So you have to show TD is parallel to BC.
Yes, and that equivalent to TD is tangent to DRS.
Yeah. Oh, and what you showed does that prove it? So like with the ratios, so okay. So let me move this down. So
Yeah, and TD is tangent to TS is equivalent to TR over TS.
yeah. So that's true. And then this is true. And then
Yeah.
this is true. Sorry, I'm just gonna. And then Trig Ceva. Okay. Oops, sorry, I didn't copy right. I copied the same thing twice. Give me a moment. So we have this, and then we copy the other thing you wrote. So then by Trig Ceva on triangle ABC, we find AR over AS equals DR over DS. Combining the above, then we have AR over AS, or we'll say DR over DS equals AR over AS. Write it like this. Is equal to TR over TS. And that means that it's tangent, right? So that implies that TD is tangent to DRS. And then we can use the radical axis theorem, and that proves that TD is tangent. And if TD is tangent, then that means TD is parallel to BC. That's just an angle chase, right? so let's think about that.
After that, OD is perpendicular to DT, so we're done.
Okay. So, sorry, say that one more time, repeat it.
Then OD is perpendicular to DT.
But then OT is perpendicular to DT, or OD is perpendicular to TD. Ah, that's a good point. So that perpendicular to TD. So yeah, so TD being tangent. So basically, I think there's still an angle chase, right? So basically, I'll write it out a little more, but an angle chase then shows that parallel to BC. Okay, Ravi says he has a projective proof, so hold on just a second. Okay, so Stefan, were you saying like this TD parallel to BC? You were saying that's just an angle chase, right?
After you
Yeah.
prove that, you can prove that TA equals TD by angle trace.
Yeah. So okay. So basically, we want to. This means that OD. This means that T and TA equals TB. Okay. Okay. So then once you know that, an angle chase is very easy to show that it's parallel. Let me just think about that. Because basically we'd show angle ADT equals angle AKB. So yeah, so I'll just write out what this angle chase is. So we have basically angle ADT equals TAB. TAB equals angle TAM. And it's easy to show that that's AKB. I think this is like the full proof. Okay, so TAM we're saying is AKB. And yeah, this is because the tangent at M is parallel to BC. All right. And then Robbie, you said you found a projective proof. So was that like using kind of the points we had before, where you draw this point over here? Sorry, your connection is cutting out a little bit. Also, you're on mute if you're trying to talk. All right, we can move on to the next problem, and then get back to the, yeah. towards the end of the session, we can go back and find the projective solution. But so yeah, this is very cool. I like the use of trig, Ceva. So here is the next problem from Komal. I forgot the shortcut to maximizing my screen. There's some keyboard shortcut to maximizing. I don't know if it's like F12 or something. F11. Okay. Why isn't it working? That's just. I think it worked last time. Oh, I had it for a sec. There we go. All right. So we have quadrilateral ABCD and a circle omega. And its sides intersect at point E. But AD and BC are, okay, so not the diagonals, but the sides. M and N are the midpoints of A, B, and CD. All right, we could do it like this. So this is E. This is M. And this is N. And these pass through the, I might as well draw O. I, J, K, L are the incenters of ABD, ABC, BCD, and CDA. So a lot of incenters here. Basically every possible triangle you could have. So I am going to draw those. So circle ABC. Sorry. This one is ABC. And then we want in circle of ABD. And in circle BCD. In circle CDA. And now J is the center of B and I is the center of E and K is the center of P and L is the center of Q. Let's close this. Those. And then we have the circles IJM and KLN. And we want to show E, U, and V are collinear. So this is pretty interesting. This would be V, and this, let me adjust the diagram just a little bit. That would be V. It's hard to see U. It's where this circle intersects it. Maybe if I draw something more like this, it'll be a little easier to see. That looks better. So this is U. All right. Definitely don't need these. Whoops. Let me move A and B down a little bit. I think it'll look a little better. Something like that. All right. Let me check the chat. IJKL is a rectangle. Huh. Is that, let's see, why is that true? You just calculate the angles and they're all 90? Okay. All right. So IJKL is a rectangle. I did not know that. BJIA and BJKC are cyclic. Oh, and that's like the proof of it, basically. Okay. All right. I'm going to hide those for now. That is good to know. Are E, M, and N collinear? I don't think so, but it could be. No, they're not. Maybe we should draw MC and MD. Okay. And yeah, no, it probably would have been a good idea to draw those because they pass through the incenters. Spiral similarity. It almost looks like these are isosceles, but I don't think they are. Or maybe they actually, but yeah, by the incenter X center lemma. Yeah, okay, so that's why it's cyclic. It's by the incenter X center lemma. MB equals MA equals MI equals MJ. And that's how you prove it all. That's cool. So a spiral similarity, like, yeah, we're saying like maybe U is the center of some spiral similarity. So yeah, UJI and UCB are similar, right? I'm just gonna check that, but pretty sure that's true. Right, the spiral similarity. Yes. So UJI is similar to UVB, and sorry, UJI is similar to UCB, and VKL is similar to VBA, and JI is equal to KL. So maybe we could do something with those ratios. Yeah, from there we can kind of get UI over VL. I'm not sure what that will do, but UIJ is not equal to UDV. No, UDC, not UDV. I think those angles should be equal. So UIJ, whoops, let me do the other one. Yeah. So MIJ, that's like a circle, because BJIA is cyclic and M is the center. So it's like a circle through the center of a circle and two of the points on the circle. So yeah, actually MJI is isosceles for that reason. Yeah. And NKL is isosceles. You guys probably knew that. And MN bisects. MN is the perpendicular bisector of both IJ and KL. Yes. That's interesting. Wonder if UV. Maybe Michael's theorem would be helpful or something. So we want to show these are collinear. Feels a lot like the radical axis theorem, right? So can we show because we know BCJK is cyclic. Like maybe we could use the radical axis theorem because obviously the rectangle's cyclic, right? So we have this rectangle, and then we have this, and then we have the circumcircle ABC. So basically, we let JK meet at a point, then this point has the same power with respect to ABC and this circle. Although I'm not sure how helpful that is. One sec, I'll be right back. All right, thanks for waiting. So yeah, E, U, and V. How do we do that? So angle UJI is UCB. Do UM, BA, and JI concur?
Yes, they do by radical axis theorem.
Ah, good point. And then we could draw the other one too. Okay. Let me just do it like this. This point homothetic centers. But yeah, we know they do, because Stefan said by the radical axis theorem. What is this point F? Did I accidentally draw another point here? I think I did. Because we have this circle. Sorry, it's like I have to draw. There we go. Oh yeah, I hid that circle, but yeah, you have to use that hidden circle. Oops. So we have this, 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 and this, and this. And yeah, we have this circle and this circle. Yeah, because then a homothety, well, is F, yeah, homothety F takes this circle to this circle, and homothety H takes this to this. And a spiral similarity takes UJI. So I wonder, I wonder what the homothety about F takes UJI to. I wonder, because it'll take it to another triangle that's similar to UCD. The incenter of I and J. The intersection of the bisector of IUJ with JI. Okay. So it's like it forms a harmonic bundle with F, I, and J, right? That point, this point. So I'm just going to hide these extra segments that I drew. So G would be the incenter. And GUF is GUF 90 degrees? Let's see. Yes. Yeah, really, it's just like you draw the perpendicular to this, and it meets at G. Then UB over UA. We want to show harmonics. That's a good way to show EU and B are collinear. Show like they're on some harmonics, harmonic quadrilateral that has three. Okay, so UB over UA is FB over FA which is JB over JA. Which let EU cut the circle at V prime. Okay. So we kind of hide this for now, and we call it V prime. Should I hide this? Yeah, why not? Okay. Z is the incenter of K and L, are G, Z, and E collinear? We have U, B. Okay. I like where Nguyen is going with this. Okay. So VC over VD is like the same idea. And then we have UB over V prime C is equal to EB over, okay, EB over EV prime. And then you combine those two. So you have to show JB over JA times IB over IA equals divided by KC over KD. Yeah, and that all seems calculatable. That's kind of what you're saying. To EB over EA. Okay, so yeah, you basically reduced it to a calculation that looks like it's just trigonometry or something. I see what you're doing. I wonder what the tangents are from E. I'm just curious. But I see what you're doing there. Yeah, so you're reducing it to something that looks like it's just a calculation, really. Let me think about how to prove. So you could call the four radiuses R1, R2, R3, R4. So JB over JA. That's basically sine B over 2 over sine BAC over 2. And then IB over IA would be something similar. And then KC over KD. Yeah, those would all be something similar. Yeah. So, okay. So I'm just gonna write it out here. So JB over JA is equal to sine BAC over 2. So over sine ABC over 2. And then IB over IA is something similar. Let me just figure out what the right angles are. The bottom one would be sine BAD over 2. The top one would be sine ABD over 2. And then KC over KD would be kind of similar. So KC over KD would be sine CBD over 2. Sorry, sine CBB over 2. That would be in the bottom. Two CBD BCD. And then, yeah, they'll eliminate. And then LC over LD. Sine CDA over sine ACDs. And then we need EB over EA. That is basically sine A over sine B. So EB over EA is sine A over sine B. Oh, okay, you wrote it out. Okay. I like that. This is awesome. Okay. All right. So, whoops, didn't copy the whole thing. So we're using the double angle formula there. So we used some trigonometry in these two proofs, but I feel like it wasn't that bad with trigonometry. Okay, so I'm going to start out right, filling in all the details. So by the incenter x sector lemma, we have MA equals MB equals MJ equals MI. So yeah, I don't even think we needed that this was a rectangle. So that means that BJIA is cyclic. And then similarly, CV and B is cyclic. And then we can apply the radical axis theorem. By the radical axis theorem, UM, JI, and AB meet at a point F. We'll say define H similarly. And then we can do the calculation that Mai wrote, where so point G we had to add. Let me move this down. It's a big diagram. Okay, so we didn't really need G. So F wait, so we're saying UB over UA is FB over FA. Okay, I'm just gonna write it out for now. Is MB equals MA. So all right, let me write this out. So we have this, and we have this. Okay. So let EU meet the circle at V prime, and then we want to show V prime equals V. V, okay. And then we have those other ratios you mentioned, which I'm going to copy in. Got to do it all at once. Okay. I'll do VMO in just a second. So, all right, combining all the above, we find VC over VD equals V prime C over V prime D. That means B prime equals V, which means that EU and V are collinear. All right, so I'm gonna move on to the next one. What time is it? 10:23. So I'll do the VMO problem now. Is it this one you were thinking of? I thought this was P4. Was P7 an inequality or something? Con sent me two different problems. Okay. We should do 7B. Okay. So, okay. Oh, okay. 7B is not an inequality. It's a synthetic problem. Was P4 easier? Or do you want to try P4 or did you already solve it? All right, let's do that looks hard, P7. Oh, you solved both of them. Okay. So you've already done it, right? Yeah, I don't like inequalities, but if you've already done both of them, do you want to just go on to another Komal problem? This one looks kind of interesting.